Nice cool fall morning for a run. Days are still hot, but the nights are definitely getting cooler and the mornings are crisp. It's a great time of year. Sunrise is later. Had to start out the run with the headlamp this morning. So our job today is to figure out why we have these seasonal changes. So let's head into the shed of science and see if we can figure that out. Shed of science. Okay, so we know that one of the major conceptions people have about the reason we have seasons is because the Earth's distance from the sun changes throughout the year. But one thing that you can point out, and if someone says that, is then how does that account for the fact that the seasons are opposite in the northern and southern hemisphere? For example, if we have winter in the northern hemisphere because the Earth is further away from the sun, then how does it make sense that at that same time it's summer in Australia? That's right, the seasons are opposite in the hemisphere. So when it's winter in the northern hemisphere, it's summer in the southern hemisphere and vice versa. So it seems pretty easy to disprove that logic that the distance from the sun causes the seasons. Now the Earth's orbit around the sun is elliptical. In other words, it's not circular, but most people have the conception that it's a really eccentric ellipse. That means a really stretched out ellipse. And it's not really like that. So most people believe that, or a lot of people believe that the sun is somewhere here and the Earth is over here in this ellipse, and this would be winter and it would be summer when we're closer. But the orbit of the Earth is actually much more circular than that. Ooh, sorry, that's not very clean, is it? And so the distance doesn't account for that difference at all. The orbit is very nearly circular. Now the Earth is a little bit further away at some times than it is at others, but that distance difference doesn't correspond to the seasonal variations. The thing that really accounts for our seasonal variations or causes them is the angle of the sun that we receive. So sunlight comes from the sun to the Earth, and you'll notice that in the wintertime the sun is much lower on the horizon than it is in the summertime. In the summertime the sun's directly overhead. In the wintertime the sun is much lower, and you can even notice that this time of year in the fall. So we're going to do an experiment to convince us that that sun angle changes the intensity of the sunlight and therefore how much heat we get from the sunlight. We're going to use a flashlight and we're going to use a light sensor, and we're going to simulate that here in the Shed of Science. Okay, that is not a flashlight, that is the sun in our setup today. And it is sending out light which is going to be incident upon our basketball Earth. It's not a basketball, it's the Earth in our experiment today. And what we're going to do is use this light sensor that is connected to our data collection device and tells us what the intensity of the light is that's being received, so we can test our idea that the angle of the sun on the Earth is the cause of the seasonal changes. So we'll set that up and we'll see how that works. Okay, here's our basketball Earth right here. And imagine that this line around it is the equator. So if the Earth is oriented like this relative to our flashlight sun down there, the light coming from the sun is directly overhead on the equator. We can use this light sensor to see how intense that light is. So I'm pointing that light sensor directly at the sun as if we were standing on the equator. And if we look at the light intensity on our instrument there, we see that it's about 220, something like that, 210 lux. That's just a unit of light intensity. Okay, now if we look back at our basketball Earth and we imagine that we're not on the equator but we're in the northern hemisphere, and we look straight up over our head, the sun's rays aren't directly overhead. They're coming to us at an angle. They're coming in at an angle. And so let's see what the light intensity is like at this angle. So if we go back to our meter, we see that it's now about 180 lux. So it's definitely lower. The light intensity is lower when the light rays aren't coming from directly overhead. Right now, they're coming directly overhead the equator, but where we are in the northern basketball hemisphere, we're looking up and the sun isn't directly overhead, it's lower on the horizon and the light intensity is less. Okay, now let's see if we can put all this together. So this is what we simulated. We have the Earth and we have light rays coming from the sun, and in our experiment the light rays were directly overhead on the equator and they were more intense there. We had 210 lux or something like that. But in the northern hemisphere, when we looked directly overhead, the sun's rays were coming in at an angle, not perpendicular to the surface of the Earth, and the light intensity was less. It was about 180 lux. So this evidence should convince you that it's the angle of the sun's rays on the Earth's surface that has to do with our seasonal variation. Now there's one more piece, and that piece is, why does the angle of the sun's rays change throughout the year? And the answer to that piece is that the Earth is tilted on its axis with respect to its orbit around the sun. This is where we have to put multiple pieces together, and this is where it gets kind of confusing for learners. So the Earth is tilted on its axis by an angle of 23.5 degrees with respect to its orbital plane around the sun. Now this is obviously not to scale. So that is the plane in which the Earth orbits the sun, which is somewhere in the center here, right? Obviously not to scale. As we rotate around, because of that axial tilt, sometimes the sun's rays are directly overhead at the equator, sometimes they're directly overhead north of the equator, that's during our summertime in the northern hemisphere, and sometimes the sun's rays are directly overhead in the southern hemisphere, and that's during our winter time. In fact, you may have heard of these imaginary lines of latitude called the Tropic of Cancer and the Tropic of Capricorn, which are 23.5 degrees south and north of the equator, and it's at those points that the sun's rays are directly overhead in winter, on the first day of winter, the first day of summer. So the reasons that we have the seasons is because the angle of incidence of the sun's rays on the Earth's surface changes throughout the year, and that changes the intensity of the sunlight we receive. And the reason that angle changes is because the Earth is tilted on its axis, so as we orbit the sun, different parts of the Earth's surface have the sun's rays directly overhead at different times of the year. Put that together with the idea that the seasons are opposite in the northern and southern hemisphere, and that should convince you and your students that it's not the distance that the Earth is from the sun that accounts for our seasons. It's the changing sun angle on the Earth's surface because of the tilt of the Earth on its axis. And that's this week's Backyard Science.